So once more, hi everybody, and thanks for joining us for today's webinar on FTIR in chemistry applications. I am joined today by Xia Stammer, who is a real expert when it comes to applying FTIR spectroscopy. She is a part of our research and development application department and will take over the second part of this webinar. In this, we're going to talk about the implementation of FTIR spectroscopy into routine chemistry. My name is Simon and I am part of the routine FTIR application team and will begin by covering some fundamentals and basics of the technique for all those of you who either need a quick refresher or are not as familiar with infrared spectroscopy compared to other techniques. Our agenda today is very simple. Chemistry gives us a beautiful structure to build upon. And although there are fringe areas like catalyst research, it is mostly quite easy to distinguish organic, inorganic, or let's say biochemistry. But even if your area of expertise is not featured here and you don't define yourself as physical, inorganic, or polymer chemist, if you are working in chemistry, we are convinced our webinar will cover topics and techniques that are of interest to you. But what is the general intent of this webinar? Well, we mainly want to do three things. First, we want this to be an informational piece. We will give a very broad overview across the FTIR applications in chemistry, and occasionally we will also dive into the application a bit to explain the greater picture a little better. By doing this, we hope to draw a clear picture of IR spectroscopy, where it is really good at, and how to apply it in your own research. Secondly, we want to showcase the unique properties of IR spectroscopy. In many labs, IR is just a means to characterize new compounds. A technique that has to be done. But many people don't see the true value of this established and well-proven technology. And for good reason. The technique is more than 50 years old and definitely not a hot topic anymore. But you might be surprised what FTIR can do. Lastly, we also want to educate our audience. Maybe you are not fully familiar with IR. Maybe you dealt with infrared spectroscopy years ago and need a little refresher. So of course, we'll briefly explain the basics of FTIR, but above all, we want to educate about the utility of IR spectroscopy. Let's start with the basics and answer the most important questions to understand the principle of IR spectroscopy. Well, what is infrared light? Infrared light is a specific part of the electromagnetic spectrum just between visible light and microwaves. To be exact, it covers the wavelength range from 0.78 to 1000 micrometers. However, we usually don't use the term wavelength a lot in IR and FTIR spectroscopy. If you look at the top of our graph, you can see the relation between energy, wavelength, and the unit we are using in IR, the wave number. And as you can see, the wave number, unlike the wavelength, is directly proportional to the energy of the radiation. This has some practical implications that we don't want to discuss in today's webinar, but just keep in mind that whenever we talk about IR spectroscopy, we are using reciprocal centimeters or wave numbers as a unit of measurement for the energy of the IR light. The IR light can be further separated into the near-infrared or NIR, covering the range from 13,000 to 4,000 wave numbers, the so-called mid-infrared from 4,000 to 400 wave numbers, and the far infrared, ranging from 400 to 5 wave numbers. However, very often, whenever the term infrared spectroscopy is used, users mainly refer to the MIR and FIR portion of the electromagnetic spectrum. Now that we know about infrared light, this brings us to our second question. How does infrared light interact with matter? In IR spectroscopy, we want to use IR light to study and characterize materials. Let's look at a simple molecule and take H2O as an example. We take IR light, direct it onto the water sample and let it pass the material. And by doing that, the IR light can trigger certain kind of vibrations in specific bonds in the molecule. This process is called absorption. On the right, you can see the most common kinds of vibration that we study with IR spectroscopy. From top to bottom, it's the symmetric and antisymmetric stretching vibration and the deformation vibration. In the early days of IR spectroscopy, this was done by going through each infrared wavelength individually, a really time-consuming process. Today, however, we use FTIR to make this a lot easier. The energy needed for this vibration is consumed in the process and therefore missing from the original IR beam. This missing information gives us clues about what kind of vibration was excited. Okay, let's get a bit more practical and talk about FTIR and the basic experimental setup. FTIR stands for Fourier Transform Infrared Spectroscopy, and actually there's a lot of benefit in using FTIR technology instead of dispersive IR instruments. However, this would go far beyond today's topic. Just remember that FTIR instruments offer higher spectral quality, collect data faster, and provide higher reproducibility because they are laser calibrated. In an FTIR experiment, a thermal source emits IR radiation across a broad range. This light is then directed at a sample to analyze it. At the sample, the IR light is absorbed, inducing vibration. Now what happens next depends on the measurement technique. The IR light can be collected in transmission, in reflectance, or using ATR. Let's regard this as a transmission measurement where the IR light will completely pass the water sample. What you see now is a transmission spectrum of our example from the last slide, water. I highlighted the typical vibrations, and from left to right you can see the symmetric stretching, the asymmetric stretching, and the deformation vibration. Now you know the fundamentals of FTIR spectroscopy, and if you want to know more on the topic, which I definitely recommend, you should check out our YouTube video on the basics of FTIR. Next, I want to cover the most important sampling techniques. Today, the standard approach to measure infrared data is using the Attenuated Total Reflectance or ATR method. But how does it work? ATR by itself is a surface-sensitive technique. Beside a source, a detector, we will need what is called an ATR crystal on which we are pressing a sample. The ATR crystal is made out of an IR transparent material, meaning IR light is not absorbed by it. The typical materials used are monolithic diamond, germanium, or zinc selenide. Now, the IR light is sent through the crystal and it will interact with a portion of the sample on top. The reason behind that is the creation of what is called an evanescent wave at the point of reflection that protrudes some micrometers into the sample material. This is quite simplified, and again, I recommend checking out our YouTube videos, in this case on ATR basics. The penetration depth of this evanescent wave, or the IR light for that matter, depends on the refractive index of the crystal material and ranges between 0.5 or 2 micrometers. So for practical aspects, it's always good to make sure the sample you are analyzing is well homogenized and the surface of the analyzed materials are clean. Compared to ATR, transmission and reflectance are somewhat more exotic in today's routine IR analysis. However, both serve special applications. While transmission is a very easy concept to grasp, reflectance might appear more complicated, so let's talk about that for a moment. The most basic form of reflection is the reflection absorption. Here we are using a reflecting background, for instance a metal mirror, to reflect the IR light behind a sample of interest. This could be a tissue section in biochemistry, very small and thin crystals, or thin layers of liquids and coatings. This is more or less a transmission measurement that offers twice the path length through a sample material. It therefore increases the spectral quality for very thin samples. The next method would be the specular reflection. Here, the IR light is directly reflected at the sample surface. During the process, some of the reflected light is absorbed, giving us information about the sample. It is important that the sample is reflective enough to provide good spectral quality. The spectra created by this method look quite different to transmission spectra and more like derivatives of the typical IR bands. This is why we need mathematical treatment of the spectra. I won't go into detail here, but because of this treatment, it is very important to only gather the specularly reflected light and not the diffusely scattered light. But of course, you can use the diffusely scattered part of the light as well to get an IR spectrum. However, this usually is often challenging and requires a lot of experimental knowledge and/or sample preparation, and it's typically applied by expert spectroscopists. However, if applied correctly, the spectral quality is excellent and diffuse reflectance IR spectroscopy, or drift spectroscopy for short, can achieve things that other techniques cannot. Examples would be in construction chemistry, where new cement compositions are optimized. But there is another method that is worth mentioning, as it is of particular interest to surface researchers. What do you do if a sample gets too thin to be analyzed by reflection absorption? The answer is grazing incidence reflection. Here we use light that is hitting the sample with an angle of incidence above 80 degrees. By doing that, we allow the IR light to have a longer optical path through the sample. This way, we can analyze ultra-thin layers and even monolayers, for example, on a functionalized surface for catalysis. Okay, that's it about the main sampling techniques. But when we talk about the basics of FTIR spectroscopy, we should also mention the concept of hyphenated or coupled techniques. Hyphenation means that we combine FTIR spectroscopy with a second technique to extend the applicability of FTIR. Examples are FTIR microscopy, thermogravimetric analysis, polarization modulated IR spectroscopy, or vibrational circular dichroism. But let's pick two examples. Microscopy, although traditionally hyphenated, has become a field of its own in recent years. The great advantage lies in the ability to characterize microscopic samples and structures chemically. A typical example from chemistry would be the analysis of single crystals or investigation of functionalized and treated surfaces. If you want to know more about FTIR microscopy, I recommend checking out our website as it features a lot of tutorial material. If you want to know more about FTIR microscopy, I definitely recommend you checking out our website because there's a lot of tutorial material on that. TG-FTIR coupling, on the other hand, is a classic workhorse in chemistry. TGA allows to monitor phase transitions and mass losses during thermal exposure, while FTIR allows you to identify and monitor the released gases. In this way, TG-FTIR can yield crucial insights into structure elucidation or characterize decomposition behaviors of polymers and pharmaceutically active molecules. Believe me, that is just a glimpse of what coupled techniques can do for you, and I hope we can dive into this topic a little further along the way when we talk about the actual applications of FTIR. Now, before we end this introduction into FTIR spectroscopy, I think we should briefly talk about teaching FTIR. Well, why, you may ask? Well, simply because it is easy to forget why infrared spectroscopy is such a vital part of a chemistry syllabus. To some of you, the spectrum on the right looks very familiar. It's the IR spectrum of HCl gas, and I guess that almost every student in chemistry has tried to calculate the isotope ratio from the spectrum at some point during their studies. But it really illustrates why IR spectroscopy has such a fundamental value in teaching and learning about scientific concepts. And besides this, it has practical use in many organic and inorganic labs where students follow synthetic routes and need to characterize intermediates. Usually this involves multiple techniques, but none so fast and safe as IR spectroscopy. The best part is that the technology is so tough that most clumsy students will easily achieve analytical success, whereas handling an NMR is a more delicate thing. But that brings me to one of the most important points, that infrared spectroscopy is not something to just torment students with. It is an actively used and very valuable analytical technique. This is especially true when one is working with constantly changing and new substances. Just think about reaction control of the first stages of a multi-step synthesis. Why wait for the result of a proton and carbon NMR when FTIR can give you the full result in less than a minute? And lastly, there is no other technique that has branched out into so many industries than IR spectroscopy. You can find FTIR spectrometers checking automotive compounds, polymer coatings, cement, gunshot residues, LEDs, OLEDs, semiconductors, microplastics, and I promise you, the list could go on forever. Whenever there is a need for a fast and simple chemical analysis, there is no way around infrared spectroscopy. And I think it is important to let students know that FTIR spectrometers no longer are these huge instruments with clumsy software. For years, software has catered to that industrial need, also benefiting researchers with a more simple means to conduct their analyses. But let's summarize what makes FTIR so valuable in chemistry applications, and after that, Shah will jump right into the applications. Above all, it is a rapid method. The sample preparation typically is minimal, depending on the technique, and in many applications, it is a universal point-and-shoot method that allows easy interpretation of sample properties with a single measurement. Another reason is the maturity of the technology. FTIR is an established and proven methodology. Honestly, we all know what to expect when we measure an IR spectrum, and although there are some surprises in FTIR analysis, they are rare and all the more exciting. It is also very easy to customize, automate, and adapt to the special needs of the user. Lastly, it is precise and highly sensitive for a lot of analytical questions. It can be used to quantify contents in liquids, solids, and gases, and if you are interested in reaction monitoring of chemical and physical processes, it can offer time resolution into the nanosecond domain. Okay, that was a lot of information. In the next part, things will be a little less theoretical, and with that, I kindly give the word to Shah Stammer.
Thank you, Simon, for the nice introductory part covering the basic principles, experimental approaches, and main benefits of the FTIR technique. Based on this, I bring you quite a few real-life application examples in the following slides to demonstrate the contribution of FTIR technique for routine chemistry. If your sample is not a metal, you can analyze it using IR. While other techniques face many limitations, IR spectroscopy is universally applicable. It doesn't care whether your sample is diamagnetic or paramagnetic, microcrystalline, liquid, or gas. Because of their compact size, FTIR spectrometers can be easily used in a glove box, or large accessories and external setups can be placed in inert atmosphere. Using an IR spectrum, you can acquire information about identity, purity, quantity, crystallinity, polymorphism, and much more. It is a comprehensive chemical analysis. That's why one of its main application examples across all facets of chemistry is basically purity control and substance verification. That box at the back of your cabinet without label, just identify it by FTIR. Or the reaction your undergraduate student did last minute, purity check by FTIR. Whether it's intermediates, starting materials, products, or byproducts, IR allows checking and identifying substances in less than 1 minute. Additionally, it can tell you basic things about coordination chemistry, especially carbonyls and cyanides, but also other ligands. You can even use it to characterize large molecular assemblies like metal organic frameworks. Here, FTIR spectra have been taken for bulk and surface-anchored Hackust MOF. The identical absorption band's position shows that the MOF has been successfully built on the surface of a carrier material without contamination. And the broadening of the bands brought the researchers to the awareness there are still residue of free ligand molecules remaining in the pores and interacting with the 3D framework, so that the crystallinity is less defined than in bulk. Anyhow, for inorganic compounds, mid-infrared spectral range is often not enough, because vibrations involving heavier atoms or lattice vibrations appear predominantly in the far infrared or terahertz region below 400 wave number. In such cases, the far infrared spectrum provides valuable additional information for identification and crystallinity check. The example spectrum has been measured for a heavy metal complex with characteristic vibrations in the far infrared region, which provides supplementary information for identification. The next one has been measured for a salt calcium sulfide, also known as gypsum. The most intense characteristic absorption bands appear in the far infrared region. And this one is a polystyrene filled with 10% titanium dioxide. The black spectrum is the pure polymer matrix. The red one is the polymer with filler material. As you see, additional bands show up in the far infrared region compared to the black one. which can then be assigned to the filler titanium oxide with the help of a library search. Furthermore, far infrared is extremely helpful for differentiation of polymorphs, meaning the same chemical compounds with fully identical mid-infrared spectrum but due to different crystalline forms featuring different far infrared spectra. Only in the far infrared region, the polymorphs can be distinguished from each other. As I said, coordination chemistry really profits from FTIR. In this example, on the upper left, the carbonyl coordination to lithium was used to assess the lithium load in a polymeric solid-state electrolyte by monitoring the CO stretching band and how it shifts and broadens during charge-discharge processes. This was simply done as a benchmark between different electrolytes. Overall, battery research is a topic that sees a lot of application from infrared spectroscopy, whether it's in fundamental research or by using spectroelectrochemistry to observe chemical reactions under electropotential changes in situ. Actually, you can use FTIR not only to study, but to identify reaction intermediates and short-lived species during reactions. Inert atmosphere is either kept by applying the measurements in the glove box directly or by using specialized equipment that allow in-situ measurements under inert conditions outside the glove box. On the right-hand side, Bruker's reaction ATR 2-in-1 accessory is shown. It is prepared to bear a customized electrochemical cell for spectroelectrochemistry studies. Again, the universal character is the main aspect here. Whether you are studying electrode materials or electrolytes or so forth, IR can work for any of them. Of course, if it is not a graphene. Of course, organic chemistry also applies IR for basic purity and identity verification, but beyond that, as IR is so sensitive to organic functional groups, it is a fast and versatile tool for reaction control and reaction monitoring. As an added bonus, it requires minimum effort and minimum amount of compounds. When you are looking at the most basic form of reaction control, our goal is only to check the reaction status and progress. We want to know whether the reaction is finished so we can continue with the next step. For this, we don't need any special solvents and we can just take a sample from the reaction, place it on an ATR crystal and measure away. This works great in the normal concentration range, but can go somewhat challenging when very low concentrations have to be measured under the excess of side products. In these cases, however, a few drops of the reaction mixture can be evaporated on the ATR crystal. There are heated options that simplify this for solvents like water or similar. If you want to follow a reaction more closely, of course, you have the option to set up something like this at the bottom left. A closed system that allows to measure spectra over time without changing the concentration. Or optical fiber probes, as shown at the bottom right, can be dipped from time to time into the reaction mixture to quickly check the status or even permanently inserted in the reaction cell for in-situ reaction monitoring. There are dedicated fibers for different spectral ranges, NIR or for MIR, and fiber probes for transmission, ATR, and reaction measurements. Overall, the switch from reaction control to reaction monitoring is fluid, and FTIR is applicable in every case, on, or offline. Whenever it should go beyond the simple "is my reaction done?" by means of reaction control, you can have an overall and real-time observation of all reaction steps using FTIR reaction monitoring. This enables to fully understand the chemical reaction, elucidation of intermediate products. To follow fast chemical processes, one spectrum can be recorded within 10 milliseconds. To be precise, over 110 spectra per second are achievable. These spectra over time can be collected, illustrated, and evaluated in modern spectroscopy software. For example, in a 3D plot, with a third axis, namely the time axis. You can easily extract the corresponding IR spectrum for a certain point of time, or consider the intensity of change of a certain absorption band over time. FTIR instruments can be equipped with reaction cells for all kinds of transmission, reflection, ATR, and drift measurement modes. Under well-defined pressure, concentration, temperature, etc., chemical reactions can be then monitored in situ. This photo shows such a setup in Inorganic National Laboratory in US. You can see the water pipe for temperature stabilization, and the vacuum line for pumping, and gas pipe for doping of reactants coming out of the Herrick praying mantis reaction cell for drift measurement. On the right-hand side, the result of a study analyzing sealed combustion activity of different rare earth materials is presented. This was a joint project of researchers from Ireland and Belgium. The in-situ drift spectra traced the formation of the intermediate bulk nitrate species, which delivers the vital evidence for the ability of this material to oxidize NO to NO2. Well, IR is powerful, but it cannot distinguish enantiomers or diastereomers. As you know, a chiral molecule exists in two enantiomers that are mirror image of each other. The one cannot be superposed on the other enantiomer, but by any combination of rotations, translations, and some conformational changes, they behave just like our left and right hands. When you take two IR spectra of them, we have measured plus and minus alpha-pinene as an example, you will receive 200% identical IR absorbance spectra. Does the power of IR really end at chirality? The answer is no. Foreign transform vibrational circular dichroism, VCD for short, can identify enantiomers and even deliver the absolute structure of chiral molecules. VCD technique makes use of the fact that one enantiomer absorbs preferred left circular polarized light and the other enantiomer rather the right circular polarized light. In VCD experiment, the difference in the absorption of left and right circular polarized light is detected, and this different spectrum is the characteristic VCD spectrum for one enantiomer. Now, it is not difficult to understand why the VCD spectrum of two pure enantiomers are mirrored at the zero line. That means where enantiomer A has a positive VCD band, the enantiomer B should theoretically show a negative VCD band at exactly the same position and with the same intensity. Furthermore, a race-mate VCD spectrum should be a zero line. And it is worthy to mention the band intensity in a VCD spectrum is significantly lower than a standard transmission measurement. It ranges from 10 to the power of minus 4 down to 10 to the power of minus 5 AU, whereas the band in an ATR spectrum is 0 point something AU, so around 1,000 times stronger than VCD. Well, let's take a closer look at the VCD spectra of 1R plus alpha-pinene and 1S minus alpha-pinene with different enantiomer excess values. The enantiomer excess factor is used in organic chemistry to express the enantiomer purity. From blue to red, we have pure 1R plus with a small share of 1S minus, then race-mate, big share of 1S, and pure 1S minus. Since the enantiomer excess factor correlates linearly with the VCD band intensity, once you have the set of VCD data for a chiral molecule, you can deduce the enantiomeric purity of your new synthesized product by measuring a VCD spectrum and doing linear regression. From organic chemistry, it is never far into polymer chemistry. Here IR is applied to monitor polymerization process. We followed the polymerization of MMA, and this is the typical outcome in our spectroscopy software. IR information can be displayed in many forms. To illustrate the possibilities, different plots are shown on the right. You can stack the spectra like on the bottom left. You can select IR bands to monitor the changes, see in the upper right. But of course, you can also generate a 3D plot, as you see here on the upper left. And of course, you can always export all spectra, all data to ASCII and CSV or other formats to create plots using softwares like Origin or GNU-plot. Now we take a closer look at the result. Every 120 millisecond spectrum has been taken. You can watch the HCC vibration slowly vanishing and a clear shift of the carbonyl vibration with advancing polymerization process. The reaction ends after about 18 minutes. Well, FTIR is a polymer analysis workhorse. Whether it is polymer itself or blends, additives, or so on. With this example, I want to highlight the universal applicability of IR that also extends to quantification in copolymers. Here, the content of styrene in SEBS copolymer has been quantified based on the characteristic bands of styrene at around 700 wave number. FTIR microscopy perfectly combines visualization of the sample surface and chemical imaging with high spatial resolution of 2 micron using ATR imaging, because every imaging pixel relates to a corresponding FTIR spectrum. In the example data shown here, the chemical composition of the sample surface and the spatial distribution of the 3 components are reviewed and illustrated nicely. Again, I would like to highlight that FTIR is not interfered by material properties like fluorescence and is universally applicable, not only for polymers, but to any spatial chemical distributions. Another hyphenated technique frequently applied in polymer chemistry is the TG FTIR, which combines thermogravimetric analysis with FTIR. The decomposition behavior of a plastic can be understood by recording the mass loss at elevated temperature, and the released gas will be identified by FTIR. Looking at the result measured for ethylene vinyl acetate, EVA for short, that is often used in the production of sport shoe soles, but also applied in textile industry, agriculture, and as a melt adhesive. You can see EVA is stable up to approximately 300 degrees C, and afterwards it decomposes in 2 steps. Acetic acid involves solely in the first mass loss step at 350 degrees C, whereas the polymer backbone, illustrated by CH vibrations, collapses within the second mass loss step at 468 degrees C after the acetic acid has been fully released. And I want to mention here that TG FTIR is widely applicable also for stability or shelf life study of medical drugs, as well as for process optimization of clay firing, of silicone manufacturing, and of 3D printing. I think that going from synthetic polymers to biopolymers like proteins is a quite nice transition. So as soon as we enter biochemistry, many different infrared applications come to mind. In this case, I first want to talk about protein analysis. Basically, there are many ways to study proteins and their properties, and if you want to look at the secondary structure of proteins, and hence the 3-dimensional form of local segments of proteins, IR spectroscopy is one of the most powerful techniques. On the right, we see a segment of 2 protein spectra, the so-called amide 1 band, which indicates the carbonyl stretching vibration, is highlighted in green. The amide 2 band on the right indicates the NH deformation vibration. By using just 2 IR signals and analyzing their form, shape, and intensity, we can learn a lot about the investigated protein. We can, as I said, investigate the secondary structure and quantity, how much alpha helix, beta sheet, or random coils is present in protein. This gives us basic information about our protein and allows us to make statements about its stability. We can also detect and monitor conformational changes in protein stability studies. This is essential if a protein formulation, buffer solution, or the excipients needs to be optimized. And of course, we can extensively study the stability of our protein under different ambient conditions and monitor aggregation, fibrillation, and precipitation. Best of all is that this works in the natural environment of a protein, in water. This might come as a surprise to many of you since it is often stated that IR and water don't mix really well. But actually, using a special setup and very sensitive detectors, we can analyze protein in very low concentration, down to 0.1 microgram per microliter. As an interesting side note, I want to mention that this technique is actually used in COVID-19 related antibody research. But the analysis of the protein itself is only a small part of biochemistry. FTIR is a viable tool for many other related applications like metabolite profiling. In a bioprocess, cells are engineered to provide us with specific compounds, for example, recombinant proteins. So naturally, it is important to create and maintain an environment where those cells can grow and metabolize nutrients optimally. To monitor and adjust those growth parameters accordingly is a field where FTIR can provide an accelerated process. At the bottom left, you can see a metabolite screening using FTIR and comparing it to the reference. You can clearly follow the process as glucose and glutamine are metabolized and lactate and ammonia are produced, all in good accordance with the reference. Additionally, we can use it to correlate growth parameters and actual protein yield after we induce the reaction. On the right side, we can see a comparison between the FTIR measurement and an enzyme-linked immunosorbent assay, or ELISA for short. Again, we see good accordance between the data with the little difference that FTIR is about factor 100 faster than ELISA. Before we go to the next topic, I think it is a good time to emphasize that FTIR can be easily automated by high-throughput methods like our Invenio coupled to an high-throughput XT. This way, you could analyze 96 metabolite profiling samples in less than 2 hours. A further example is about homogeneous catalysis in biochemistry. The alpha chymotrypsin catalyzed hydraulic cleavage of peptide bonds at the carboxyl site of aromatic residues is monitored here. FTIR rapid scan has been combined with the so-called stop flow technique. The fast scanning mode of FTIR allows to follow the fast reaction, and the stop flow cell allows very precise volume shot and fast mixing of reactant. It triggers the start of FTIR measurement. This was mandatory because reaction ends up within seconds. The result is presented here. The formation of the product can be followed by the increase of the two absorption bands at 1604 and 1322 wave number and the decrease at 1344 wave number, indicating the formation of a new C-terminated carboxylate group. Diffuse reflectant infrared Fourier transform spectroscopy, (DRIFT for short), is the method of the choice for heterogeneous catalysis, for example, to study loading process, and finds therefore application in chemical engineering. In the example experiment shown here, nanoparticle of CR oxide has been doped with europium and coated with gold. The CO gas loading has been followed by FTIR for doped and undoped CR oxide particles. The CO band intensity over time reveals the loading amount. It came out europium doping reduces the catalysis activity and the total loading amount. The reason behind was less spectacular. The doped particles exhibit bigger average particle size and catalysis activity reduces with the decreasing surface to volume ratio. Anyhow, FTIR helped to deliver this conclusive evidence. Catalysis research is also done in physical chemistry, but in a more fundamental manner. Model systems are investigated which simulate a real catalysis process, but are kept easier and much better to be controlled. Powder catalysis are replaced by single crystals of the same compound, reaction chamber replaced by UHV chamber. By doing so, reaction conditions, catalysis ingredients, and structure can be fine-tuned and perfectly controlled. This is a great help to selectively analyze the influence of every single parameter and to fully understand every single step of the whole heterogeneous catalysis process. Only with this knowledge, we can optimize the catalysis to higher efficiency and lower cost in, for example, technical chemistry. In the example shown here, the surface catalyzed formation of formaldehyde has been considered, especially the CO adsorption onto titanium oxide catalysis surface, which is an essential step of the surface catalysis. A catalyzed reaction has been checked in detail. I want to point out we are measuring in reflection mode the adsorbed CO molecule with sub-monolayer surface coverage and the absorption band appearing at 2174 wave number with intensity of about 10 to the power of -5 AU evidenced at the adsorbed CO species. This has been done for perfect and defect. Here's the defect shown here. This has been done for perfect and defect titanium oxide surface. A comparison of FTIR spectra shows the defect catalysts show higher activity and the defect concentration, which is well controlled in UHV chamber, correlates with the product yield. Anyhow, it was a long story. At the end, the researchers were able to bridge the gap between the model system and real catalyst and receive, using the shown UHV FTIR setup here, comparable result for single crystal and powder titanium oxide. Surface immobilization and functionalization is still a central subject in physical chemistry since it delivers fundamentals for sensoric, biocompatibility, catalysis, and many more application fields. We analyze here silane modified surface by IRAS. This surface layer is an ultra-thin monomolecular layer with a thickness of around 2 nanometer. The film quality can be indicated by IRAS using linear polarized light. Based on the surface selection rules and with help of computer simulations, it is possible for many well-ordered layers to determine the molecular orientation and packing density. I won't go into details here. In this project, the preparation parameter of this monolayer has been optimized by FTIR since the monolayer has been characterized well in the past using IR, and the IR spectra were well known. Well, that were basically all examples I want to show you today. We could highlight the universality, versatility, and simplicity of FTIR spectroscopy and scratched the surface of what is possible. Your take-home message is that FTIR works for almost any sample, is applicable in situ, and has a real major base of knowledge. If you need reference data for your experiment, you're very likely to find it in the decades worth of publications that deal with FTIR technique. So all that's left to say is thank you for listening, and I guess that Simon already gathered some questions for our Q&A session.